Now that we have a basic understanding of what a system of equations is, let's take a look at how to solve systems of linear equations. There are three algebraic methods that we're going to look at this week, and those three methods are graphing, substitution, and elimination. Now, graphing is my least favorite because if I'm doing it by hand, it's only as good as how precise I can draw my graph, and since I'm using a computer screen without a ruler, obviously it's not going to be pretty. So what I really want you to do is when we do our next example, we're going to use Desmos. I want you to use Desmos as you're working this week as a way to check your work. So I wouldn't do it to just find the answer because when you're doing a question for me, say on an assessment, I'm going to make you show all of your work. So when we do substitution and elimination in a little bit, those are the types of methods I'm going to be looking for, but please use graphing to check your work and make sure you're on the right track. So I'm going to graph both of these, and these are both in linear form. The first is in slope-intercept form, the second is in standard form. So to graph the first one, I am going to start at -6 on the y-axis. My slope is -3/1. That means go down 3 to the right one, or up 3 to the left one. Now, because I don't have a ruler, and again, I'm using a computer screen and I have just an inability to draw a nice straight line, I'm going to make several points. If you're doing this on paper, please feel free to use a ruler. I just wanted to make sure I don't completely murder this line. It's going to look something like this. And again, I'm interested in the point at which these two cross. The second one, this is standard form equation, and typically I would use that cover-up trick on a standard form equation, but because if I used the cover-up trick, I would get 2x equals 1 as my first point, which would be a fraction, I'm just going to turn it into slope-intercept form. So I'm going to subtract 2x from each side to get -y equals -2x plus 1. I'm going to divide by -1 to get y equals +2x minus 1. So now I'm going to put the point -1, use the slope of 2 to go up 2 over 1, or down 2 to the left 1. So we can see I just found the point at which those two are going to cross. I'll go ahead and connect the points, but the solution to the system would be this point at which they cross. So my solution is -1, -3, which is this point right here where the two lines cross. For my next two equations, I really want to look at using Desmos because it's more precise, it's a lot faster, and again, I encourage you to use Desmos or whatever your favorite graphing utility is as a check as you're working this week. So I'm going to start entering these equations as I talk, but remember that I will be very interested in not just what is the solution, but how did you find the solution. So in a minute, we're going to talk about how to algebraically solve for the point at which they cross. That is what I'll be looking for. So here I have graphed my first system of equations, y equals 1/2 x minus 2, and -2x plus 4y equals 8. And I can see by graphing those that they are in fact parallel lines. I would be able to tell that if they were both in slope-intercept form, I could compare those two slopes, but because they weren't, I graph this and see they don't cross, so the solution to my first system would be that there is no solution. For my second system, I've got y equals -1/4, use that arrow to move out of the fraction, 1/4 x plus 2, so there's that green line. I'm now going to graph x plus 4y equals 8. And as we can see, I have graphed both lines. So let me take away the green for a minute, it's just orange. Let me take away the orange for a minute, it's just green. We can see that those two lines are exactly the same. So what would be the solution to this system? It would be that I have infinitely many solutions. We're now going to look at substitution and then elimination, which are the algebraic methods that you'll want to focus on this week. We will be using the exact same three systems that we used with graphing, so we should get a solution for one and no solution for another, and an infinitely many solutions for the last. I've included this slide for you, and I'm not going to read it, just as a good reference. So these are the steps that we'll be following together, but I'm not going to read through this. I'm just going to take you through the steps on our next example. So typically you will have a choice choosing substitution or elimination. So when I choose substitution is when I already have a variable that is isolated, or that I can get there easily. So in this case, as you can see, y is isolated. Isolated, of course, means all by itself. So since y is by itself, it's isolated. That's the variable I'm going to use for substitution. For substitution, what I'll do is whatever one is isolated, I'm going to then put a parentheses around what it's equal to. I'm going to take the other equation, in this case 2x minus y equals 1, and I'm going to substitute the stuff in the parentheses. So 2x minus, instead of y, because remember I'm looking at those two things being equal, y and y, 2x minus negative 3x minus 6 equals 1. So I've replaced y with the parentheses. And notice when I put it into my equation, I used parentheses. And the reason for that is if I don't, it's really easy to mess up because I've got all of these negatives here. And if I don't do that, it's really easy to mess that up. So now, as you can see, using substitution, I only have one variable. I have the variable x. So now I'm going to solve for that variable x. So I have 2x, I have minus negative 3x, so that's plus positive 3x. And then I had minus negative 6, so plus positive 6, equals 1. Now everything's out of parentheses. I can combine things together. 2x plus 3x is 5x, plus 6 equals 1. Subtract 6 from each side. Divide by 5. So what I have solved for is, remember, my solution to a system is an ordered pair, typically, or no solution or infinitely many. But because I have x equals negative 1, that is the x value of my solution. Then I'm going to look, and remember previously when we did this, we did get the point negative 1 comma negative 3. So that's what I'm hoping I'm going to get again. Then I'm going to take either one of these equations and plug in the negative 1 for x. And what I find is whichever one I used for substitution is usually the easier one. So y equals negative 3 times, instead of x, negative 1 minus 6. Negative 3 times negative 1 is positive 3. 3 minus 6 is negative 3. So my solution, and I would always write it as an ordered pair, is negative 1 comma negative 3. We're going to do these next two examples to see what happens. Remember, one of these should be a no solution and one an infinitely many. So let's take a look. Again, in this first one, I already have a variable that's isolated. The y is isolated. And it's not always the y that's going to be isolated, so don't feel like you have to use y each time. But now I'm going to take negative 2x plus 4. Instead of y, I'm writing 1/2 x minus 2 equals 8. And now I'm simply going to solve. Negative 2x, I get 4 times 1/2, which is 2x. 4 times minus 2 is minus 8, and then equals 8. And so negative 2 and positive 2 cancel, and that just gives me negative 8 equals 8. And because that is not true, whenever it's not true, so the variable is going to go away in actually both of these examples, but whenever I get something that's not true, that means there is no solution. So remember, when we did this before, this was the parallel lines where we had no solution. The other example, again, is already set up very well for substitution because I've got the minus 14x plus 2 all by itself. So again, y is the variable that I'm going to use. I'm going to get x plus 4 times negative 1/4 x plus 2. I'm substituting what y is equal to, rewriting the equation. That gives me x. 4 times negative 1/4 is negative 1x. 4 times 2 is 8. And so again, if I look at what's happening here, this is a positive 1x and a negative 1x which cancel, so I really just get 8 equals 8, which of course is true. So when the variable goes away, but my whatever's left over is true, this is the infinitely many solutions, which means if I graphed these are the exact same line twice. Last up is elimination. And the way that I have these equations set up, they're not set up well for elimination. So in the real world, if I were asked to solve these, I would not use elimination. But here are the steps. Again, I'm not going to go through the steps with you. I'm going to go through them with you as we go through our next example together. So here I have a system, and they want me specifically to use elimination. And the reason I said before that I wouldn't use elimination is because I really want my equations in the same form. So if they're in the same form, elimination is easy to use. As you can see, they're not. This first guy is in slope-intercept form, and the second guy is in standard form. So what I have to do is do extra work to turn them into the same form. So I'm going to turn this equation by adding 3x to each side into 3x plus y equals negative 6. My second equation is going to remain exactly the same. So now as we can see, I have these in the same form. So elimination is actually my favorite of the three, if it's already set up well. And what we're looking for in elimination is I want to, and notice I've got x's lined up, and I've got y's lined up, and I've got constants lined up. So that's what you need for elimination. And what I really want to have happen, and I do have it here, is I want in one of those columns to have the exact same coefficient. And when I say one of these columns, I mean one of these two. We don't care about this one. In one of the variable columns, I want the same coefficient, that's the number in front of the x or the y, same number, opposite sign. So here I have a 3, here I have a 2, that's not the same number. And it's not the same, it's not the opposite sign. Here I have a positive 1, and here I have a negative 1. So it's the same number, 1, one's positive, one's negative. So that makes me really happy, because now I can just add these together. So 3x plus 2x is 5x. Positive 1y and negative 1y is 0y. That's why it's called elimination, because by adding them together, something's going to eliminate. Negative 6 plus 1 is 5. Divide each side by 5, because now I just have one variable, and I get x equals 1. Now let's try, oops, I thought that was wrong. This is negative 5, because it was a negative 6. So x is negative 1, because remember previously we had the answer negative 1, negative 3, and that's where I should get to again. Just like we did with substitution, now I'm just going to take this answer and substitute it back into one of my original equations. And it doesn't matter which one. I'm going to choose that first one again. So y equals negative 3 times negative 1 minus 6. Y equals positive 3 minus 6. Y equals negative 3. So I did end up with the same solution, but again, be careful so you don't make that same mistake I almost did on my x. Now again, here's those same two that we did before, and remember when we did them before, this was no solution, and this one was infinitely many. So let's take a look at if we get those again. Just like I did on the last one, I'm going to turn this into standard form, so negative 1/2 x plus y equals negative 2. Negative 2x plus 4y equals 8. So this one's a little bit harder, because if I look at that same thing that I did before, and I'm looking at x's lined up and y's lined up, I don't have the same number on either. So I've got 1/2 and 2 both negative, and I've got 1 and 4 both positive. So what I'm going to have to do here is take it to the next level, which means I'm going to have to multiply an equation by some constant first, because if I added them together right now, I would get negative 2.5x plus 5y equals 6. And did that do anything for me? No, it didn't, because I still have an x and a y. So what I need to do is I need to determine which one I want to get rid of. So a lot of people are scared of fractions, so I'm just going to stay away from that one. I'm going to look at the yellow column and say, how can I make those numbers the same number with the opposite sign? Well, I already have a 4 here. So what if I took this whole equation, the first equation, times a negative 4? So if I took negative 4 times negative 1/2, I would end up with positive 2x. If I took negative 4 times positive y, I would get negative 4y. And if I took negative 4 times negative 2, I would get positive 8. And then I'm just going to recopy that second equation. And now, if I look at those columns, I have same number, opposite sign, and I have same number, opposite sign. So as we can see, what's going to happen here is I'm going to end up with 0 and 0 equals 16, which again is false, which is where we get no solution or the empty set. We're going to do the same thing with the second one. Again, we've got fractions here, so we're probably going to have to end up doing kind of the same thing. This guy is going to turn into positive 1/4 x plus y just by adding 1/4 x to each side. This guy didn't do anything. Just like last time, if I look at my columns, I don't have the same number, and I don't have the same number. Again, if you're scared of fractions, then let's look at the yellow column. And in the yellow column, I have a 1 and a 4. And I know I could take 1 times negative 4 to make it negative 4. So I would have a negative 4 and a positive 4. So just like on my last example, I'm going to multiply this whole equation by negative 4. That's going to give me negative 4 times 1/4 is negative 1x. Negative 4 times positive y is negative 4y. Negative 4 times positive 2 is negative 8. And then just recopy that second equation just as it was. I didn't touch that one. Now, if I look at my columns, I have same number, opposite sign. And again, typically that's not going to happen where they both cancel out, but in this case they did. So these guys would cancel, these guys would cancel. I would get 0 equals negative 8 plus 8 is 0. Because that's true, that's infinitely many solutions.